Rayleigh's principle utilizes the principle of conservation of energy to determine the first mode and fundamental frequency of structure. In a closed system, the amount of energy remains the same, just that it may change from one form to another. When structure is moving, its kinetic energy is the greatest. Meanwhile, when structure reaches its maximum displacement, the elastic strain energy is the highest at that instance. Therefore, assuming no energy loss takes place in the process, total kinetic energy equals to total elastic strain energy. From here, let us express the displacement as A sine omega nt and velocity as A omega n cosine omega nt. Under the most critical condition, displacement would equal to A and velocity would be A omega n. After substituting both terms into the equilibrium equation for energy, we may express the square of natural frequency in terms of other parameters. The force of stiffness can be written based on Hooke's law, and in a closed system it would be equal to inertial force as well. We can then make some substitution based on this condition and simplify the equation for omega n squared. Rayleigh's principle requires the story displacement data to solve for a structure's fundamental frequency. From the force correlation we established earlier on, the displacement equals to the inverse of stiffness times inertial force, which we may also rewrite as mg. Recalling the MDOF system we used in iterative method example, let's solve for its fundamental frequency by using what we got here. First, we determine the displacement of each degree of freedom by multiplying inverse k and mg. We may square the displacement to ease our next step. Then, we may take the mass components for each degree of freedom and substitute them into the equation accordingly. The square root of the result will be the fundamental frequency of structure. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.